All right, welcome back. Today we are going to talk about batteries. So continuing our electricity topic, we are going to talk about batteries. And of course, we can't talk about batteries unless we start talking about where they came from, their history, and all that jazz. So back in the day, the first battery ever was first demonstrated to the public in 1800 by a scientist named Count Alessandro Volta. Okay, so Volta was the first guy ever to come up with our battery, and our battery looked nothing like the battery we have today. Okay, so his work was again inspired by someone else named Luigi Galvani, and Galvani studied biology and found that actually if you touch a piece of metal hooked up to a wire to a dissected frog's leg, you could actually make it twitch. So Galvani was working in the biology, hooked some things up, and when he poked the metal to the leg, the frog would twitch. And he figured, well, you know what? Electricity must be able to be found within animals. And Volta didn't totally agree with that. He said, yeah, that has to do with electricity, but it's probably more to do with the metals than the animals themselves. So we continued to work on it, and came up with our first battery. So through his research, he found different experiments and he conducted them all, and he found that different metals in contact with each other can create electricity. So if you had one certain type of metal and you brought it in contact with a different certain type of metal, then you can get an electric current to go ahead and start happening. So what he did with this information is he's like, you know what? I'm going to make just a stack of these different layers of metals. I'm going to have zinc metal, and I'm going to have silver or copper, whatever one that was readily available. And what he also did is not only did he stack those and alternate them, but he had this thing called a blotting paper. And he soaked that paper with salt water in between those two metals. And if you think about it, when we talked about conductors, we said, well, salt water is a fantastic conductor. So that's why he would have used salt water or the blotting paper soaked in salt water, right? Because you can't just pour salt water on the metals and call it a day. You need to have it confined to a space. So we figured if you soak the paper in that salt water, you get the conductivity of that salt water, but the single space required from the blotting paper. Okay, so we stacked all of these metals together with the blotting paper in between, and when he used a wire, he connected the top of the stack to the bottom of the stack, which created a closed circuit. Right? In our last lesson, we talked about how important it is to have a closed circuit, because without a closed circuit, you can't have any current electricity, right? Because the current or the electrons need to have a closed path in order to be traveled or to travel through that circuit. Okay, so what he did was he stacked them all up, had the salt water blotting paper in between, and then attached a wire from the top of the stack to the bottom of the stack. Well, what was pretty cool is that he was actually able to measure a voltage and a current, right? And we know that you could measure current using an ammeter, okay? He figured out that the higher he stacked the pile, the higher the voltage as well. So through trial and error, he was able to discover that not only did the metals have a lot to do with electricity, but we could get that electricity to have a higher voltage by doing more and more and more stacks of those metals with the blotting paper in between. So this is something what obviously the colors are a little bit different, but this is a kind of an idea of what his battery would have looked like, right? He had the zinc here is represented by the blue disc, the silver is represented by that red disc, and the blotting paper that is soaked in salt water is represented by that white piece there. And then here we have the top of his stack and the bottom of his stack. And what he did is he would have connected the top and the bottom with a wire. And through that, if he popped in an ammeter, he was able to discover or read a current. And if he popped in a voltmeter, he was able to discover the voltage. So when we say that he was able to figure out that the voltage increased the higher he stacked the battery pile there, he was measuring that on a voltmeter. All right. So continuing on, the current that Volta discovered is produced because of the chemical reaction happening between the two metals. So the zinc and the silver, or we said the zinc and the copper, is actually chemically reacting to each other, and that is what's causing the electricity to travel, right? So zinc is a metal, and it's actually willing to lose its electrons. While copper or silver is also a metal, but those specific types of metals often want to attract those electrons, right? And if you think back to our chemistry unit, a little bit similar to ionic bonds. It's not an ionic bond in this case because we have zinc and copper, zinc and silver, and those are all metals. But similar in the sense that one wants electrons and one wants to lose electrons. So if one wants to gain and one wants to lose, those electrons will be traveling from one to the other. Okay? When the two metals are connected in a closed circuit, so through that wire, the electrons will travel from the zinc towards the copper. So the electrons travel from the zinc towards the copper, creating a current or a flow of electrical charge over time. And that current is produced and then could be used to power things. We could use that to power light bulbs. We could use that to power motors or fans or anything that we kind of wanted. Of course, the batteries that they had back then were probably not as efficient or as small or as high-powered as the ones that we have today, so keep everything in mind. But these pictures here are actual pictures of what the batteries would have looked like. And of course, they would have been a lot bigger than what our batteries look like today. So they could have been like the size of a water bottle, but also larger if you wanted a higher voltage. But that is what that kind of original idea came from. So there's a chemical reaction happening between the metals. That is why the electrons are flowing. Okay. Volta's original battery was called the voltaic pile. And you see here kind of just an idea for size in the picture. This is the battery that they had. And you notice this battery was huge. Okay? So with that being said, that's kind of an idea of what it looked like. It's called the voltaic pile. Actually, the French word for battery is pile. So if you think about it and their ancestry, kind of makes sense where that comes from. Even though those voltaic piles, those original batteries were super huge, super bulky, they provided the only practical source of electricity in the early 19th century. Okay, so a lot of the other electricity they had back then wasn't really useful, it wasn't really practical. It's not like we have today where we can just plug in our device to an outlet in the wall. So this was a huge discovery. Okay. Similarly, we have modern batteries. So this is a kind of what our modern batteries look like. We have a bunch of different brands and things like that. So obviously the color is going to vary, but our batteries typically look very similar to each other, not to the old one. The voltaic pile remained in the lab, and it was studied for years. And then eventually, when we had the telegraph and the telephone created, well, they're saying, well, we need more electric power, and we need something more reliable as well. It's not okay that this old battery only lasts for so long, or sometimes if there's not enough salt water on the blotting paper, it doesn't work as well as it should. So they figured, you know what, we have to create something more useful so that we could use the telegraph and the telephone more efficiently, and that is when they started with experimentation and got to something called the dry cell, or the battery that we see today. And that was invented in the 1860s, so quite a long time ago, and its primary purpose was for the telegraph. Right? And if you think about it, a lot of advancement in science and even a lot of advancement in math is due to our change in the world. So once we have something invented, we want to perfect it, we want to make it better, so that drives science forward, and that's what happened with the battery, right? Because we had the telegraph, we wanted to make it better and better and better, and so in the 1860s, we came up with this dry cell battery. The dry cell is not actually completely dry. It's not like the voltaic pile where you could literally touch the blotting paper and feel that wetness of the salt water. But on the outside, our modern day battery is in fact dry. On the inside, however, there's actually a carbon rod. So this here in the middle, that is our carbon rod. It is made of our element carbon. And then we have this stuff here. So we have on either side are fully surrounding that carbon rod in the middle. We have this paste, which is kind of cool. The exterior of the container, exterior of the battery is made of zinc. Okay, so the outer piece is made of zinc. So we actually don't use silver or copper very much in our batteries today. Zinc carbon is pretty popular, although obviously you might have heard of lithium batteries or things like that as well. The batteries vary in what they use depending on the make and model that the company producing those batteries prefers, but zinc carbon is very common. So the zinc is the metal on the outside, carbon is on the inside, and it is separated by a paste. What that paste does is that it actually prevents the electrons from traveling from, you can't really see that. Let me try a different color. This paste here, the paste that's located here, prevents the electrons from traveling from the zinc to the carbon rod. Because we don't want all of that electricity to just happen within the battery, we want the battery then to power other devices. So what happens is we connect a wire from the zinc to the carbon. The electrons that want to leave the zinc can, and they travel through the wire all the way around to get to the carbon rod, right? And that flow of electrons is really what electricity is all about. And if we pop on something, let's say we pop on a light bulb partway through, we could actually power that light bulb because the electrons will travel through it. So the whole purpose of this paste is so that the electrons don't take a shortcut and just immediately jump to the middle, because otherwise that's not going to be useful for us. Okay? So electrons travel from the zinc to the carbon rod, which then conducts those electrons outside of the cell through a wire in order to power a device. In our batteries, the bottom terminal is called the negative terminal, so that's the negative part of the battery. Oftentimes, when you see a battery, it's actually labeled, so the top will be positive, the bottom will be negative. And then the top terminal is called the positive terminal. Okay? When a circuit connects the positive and the negative terminal, so we connect a wire from the bottom to the top or the top to the bottom, the electrons at the negative terminal, so all the electrons that are here, will flow to the top. Okay? The flow of electrons is what causes that electric current, or is called an electric current. Now, the one thing to keep in mind is if you ever take a look at any sort of diagrams, we know that batteries, the electric charges travel from the negative to the positive, right? Because the negative is where all the electrons are right now. They attract to the positive end because opposite charges attract. And so what actually happens is that we have electrons here and they travel around my circuit. And they go all the way to the positive. So they are going from negative to positive. Engineers, they actually didn't know that the electrons were negatively charged. The world didn't know electrons were negatively charged, but engineers were doing some awesome things throughout the world. And so they said, we have to figure out a way in which they travel. I don't know, what do you think? And they said, you know what? Let's just say that it flows from positive to negative. So engineers often in diagrams will say it flows from positive to negative. That is technically incorrect. It's not that engineers don't know that now. It's just that at this point, engineers have done so much that to go back and to change all of the work so that the diagrams are accurately representing what is literally happening with the electrons seems like a lot of effort. So their diagrams are consistent in the sense that they always draw it from positive to negative, but they know that that is not true. Okay, so the engineering diagrams will show something like this here, in which the electrons flow from the positive to negative. We know that that's not actually correct. However, if you look online, you look up images, you might still see images that reflect that. And again, that's just because they were doing these diagrams before they knew the electrons were negatively charged. And they knew that the electrons were the particles that carried that electric current, but they didn't know if they were positive or negative, so they guessed and happened to be wrong. So this is what's actually happening here. All right. What we have here is we have 3 different videos, and I'd really, really appreciate it if you could watch all 3 of them. So you can't click on them on the link, or you can't click on them in the video, but if you go onto Teams with the PowerPoint there, you should be able to click on the links in the PowerPoint slides, and they're all pretty short videos. They're kind of cool in the sense that they explain how batteries work. They explain a little bit about rechargeable batteries, and they talk about batteries and how bad they are for the environment. So this last one is especially interesting because what it says, a little bit of a spoiler, is that one battery, if it's not properly recycled, can pollute up to 400 liters of water, which is so much, and considering how small a battery is, which kind of leads us to our next point here, which talks about recycling batteries. Okay, so oftentimes if you have batteries maybe in your TV remote, maybe in your parents' vehicles, or maybe in your calculator, something like that, oftentimes when we replace them, we just throw them out in the trash. And throwing them out in the trash, yeah, you dispose of them, but that chemical inside of the battery, that paste that's located between the zinc and the carbon, that's actually really, really bad for the environment. So there's places like Recycle Manitoba, which is a website, and they could actually tell you where in your city you will be able to recycle batteries, but also other household goods. So recycling is super important. I am definitely a fan. You want to make sure that you're not just throwing out your batteries. So we are going to look at different places on this website to see how and where we can recycle different items so that now that we are better informed, we can do good work for the environment. Okay? So if I click this link here, it takes me to this website. So this is recyclemanitoba.ca. And this is a little bit of what the website looks like. I'll invite you to browse it a little bit more on your own. But what its purpose is just for you to find a place to recycle all of your goods. So say, for example, we want to recycle batteries. Here in the middle, when it says find a collection site, it says, what do you want to select? So what material do we want to recycle? So we might have electronics, we might have fluorescent lights. There's all these things that aren't typical recyclable items like glass and paper and things like that, that of course we want to make sure doesn't end up in our landfill. So if we click single-use batteries, then we can figure out which ones. Well, do we have alkali batteries? Do we have lithium batteries? So alkali batteries are the ones that you'll probably have. So those are your AA, AAA, C, D, and so on and so forth. So I'm going to say, let's say we have some AA batteries here. And where are we located? Since this is Recycle Manitoba, it lists all of the Manitoban major cities and areas. So we're going to click Winnipeg because that's where we are. And what happens is it actually just starts giving us a list of all these different places around the city of where we can go and recycle them, which is absolutely amazing. Right? So we have Advance Automotive, we have Alcom Electronics, Best Buy on Pembina will take them, Canadian Tire on Regent, and Vermilion, and Keniston, and McPhillips. They will all take your recycled batteries, and look at all of these different pages where you can just figure out where to recycle. We can also, if we type in the school's address here, so 550 Wellington Crescent, and hit go, it will actually tell us our closest point. So Monroe Library, oh, hold on, does that tell us our closest place? That does not. We could kind of play around with it, but it will show us on the map in relation to where we are, so we can see how close or how far things are. So some of them are further than necessary, but once we find something that's relatively close, we might say, hey, let's go ahead and recycle our batteries there. And again, you could plug in your home address if you wish. Maybe you could find a location that's close to you. But recycling is a fantastic thing to do, and getting in the habit and telling your parents about it and telling your friends about it is super, super important so that we could do our part to better the environment. Not just batteries. I'm going to do a little pitch here for recycling other things too, right? You might have lead acid batteries, which aren't good to leave in our environment. Oil and antifreeze, so things like once your parents get an oil change of their car, that can't just be drained down. Paint, so maybe you painted a room in your house, you have some left over, or the paint went bad. You don't want to just chuck that. You want to recycle it appropriately. Tires, maybe your parents' car tires or your bike tires have worn out. You want to get rid of them, right? This website is an absolutely fantastic resource so that you can recycle appropriately throughout the city. Anyways, we are going to end our lesson off with that, my little pitch. Please watch those 3 videos, take a look at Recycle Manitoba, start collecting all of your batteries so that you could recycle them, and otherwise, have an absolutely wonderful day. Peace out.